As an introduction to second order differential equations, we want to begin by just checking solutions to a second order differential equation. And then we'll look also at finding a particular solution given initial conditions for the same differential equation. So here, I'll read this through. So we want to verify that y1 equals e to the x, and y2 equals e to the 2x, and y of x equals c1 times y1 plus c2 times y2 are all solutions to the differential equation y double prime minus 3y prime plus 2y equals 0. We then want to find a specific solution of the form y of x equals c1 y1 plus c2 y2, which satisfies the initial conditions y of 0 equals 1 and y prime of 0 equals 0. So let's start by noting that this is our second order differential equation. This is a second order differential equation. And it's called a second order differential equation since it has a second derivative in it. So that makes it second order. This is also called a homogeneous, always mess that up, homogeneous second order differential equation. And that's because it is of the form ay double prime plus by prime plus cy equals 0, with the equaling 0 being key to the word homogeneous. Okay, so we want to start by confirming that y1 is a solution to this. So to confirm that y1 is a solution to the differential equation, we are going to find its derivatives, its first and second derivatives, because we need to plug them all into the differential equation. Now that I have these derivatives, y equals e to the x has derivatives of e to the x and second derivative of e to the x as well. And so we'll take these and plug them into y1 double prime minus 3y1 prime plus 2y1. And we want to say, is that going to equal 0? We're going to need a bit of space here. So when I plug these in, I get e to the x minus 3e to the, e to the x plus 2e to the x. We're wondering if that equals 0. Combining like terms on the left does in fact result in 0, equaling 0. So yes, y1 is a solution to the differential equation. Now, y2 equals e to the 2x. We want to check if this is a solution. When we take derivatives here, we get y2 prime equals 2e to the 2x, and y2 double prime equals 4e to the 2x. We take these and plug them into the differential equation, y2 double prime minus 3y2 prime plus 2y2, and we ask, does that end up equaling 0? If it does, then we have a solution. So y2 double prime is 4e to the 2x minus 3 times y2 prime is 2e to the 2x plus 2y2, that is 2e to the 2x. Now, does that equal 0? We have 4 minus 6 is negative 2 plus 2 is, in fact, 0. So yes, y2 is also a solution to the differential equation. And this is always going to happen for second order differential equations, is that we'll have two linearly independent solutions. So second order differential equations will have two linearly independent solutions. And what that means for our purposes is essentially that they aren't scalar multiples of each other. If I graphed y equals e to the x and y, and then y2 equals e to the 2x, and then I just looked at those two graphs, I couldn't put a multiple of one and get the graph of the other, right? There's no way of just multiplying e to the x by a number to get the same graph as e to the 2x. So they are linearly independent, meaning they're for just two equations, they are not multiples of each other. Now we're not going to go into it today, but for a third order differential equation, we would have three linearly independent solutions. And for fourth order differential equations, we would have four, and so on and so forth. And linearly independent in those is going to have a little bit more of a technical definition that we would take from a linear algebra class. So we don't need to get into that today, so we're going to just kind of avoid that conversation for now and focus in on just these second order differential equations. We're noting here that this second order differential equation does in fact have two distinct solutions, e to the x and e to the 2x. We're then going to look at linear combinations of these two solutions. So y of x equals c1 e to the x, that's y1, plus c2 e to the 2x. And we want to see that this linear combination is also going to be a solution. And this is not just one linear combination, this is all of the linear combinations combined with the c1 and c2. So as we do this, we'll get our derivatives. Y prime of x equals c1 e to the x plus c2 e to the 2x. And then y double prime of x will equal c1 e to the x plus 4c2 e to the 2x. And if we want to check, is this, I'm going to give this a subscript of g for general solution. This is the general solution here. So y sub g double prime minus 3y sub g prime plus 2y sub g. Does this add up to 0 as well? So this is going to take a little space here. Come on. Y sub g double prime is going to be c1 e to the x plus 4c2 e to the 2x minus 3 times c1 e to the x plus 2c2 e to the 2x, and plus 2 times the original y sub g, c1 e to the x plus c2 e to the 2x. Does that add up to 0? So we're going to rearrange these. We're going to get a c1 times e to the x minus 3e to the x plus 2e to the x. And this is what we got when we plugged in y1 right here. This is y1 double prime minus 3y1 plus 2, minus 3y1 prime plus 2y1. And then here we'll factor out a c2 as well and combine the e to the 2x's. We'll have 4e to the 2x plus, sorry, I missed minus 6. There it is. E to the 2x. I do the minus 3 times the 2 here. And then plus 2e to the 2x. And this is what we got over here for y2, was that same thing. We saw that that will also equal 0. Back out. So this other one we got over here, this is y1 double prime minus 3y1 prime plus 2y1. So this adds up to 0 as well by our previous work. So So when we ask, does this equal 0? The answer is 0 plus 0 equals 0 is a yes. So this also is a solution. Not only is this, but all solutions of this form for any constant C1 and C2 will also work. So if we have two linearly independent solutions, then we can add up linear combinations, any multiple of the first plus a multiple of any multiple of the second, and that will still give us a solution to the differential equation. This is always going to work. So we'll make a note of that here, is given two linearly independent solutions to a second order homogeneous differential equation. The general solution is all linear combinations of the two solutions. Cool. I'm going to move this just a hair here. All right. So we have one other thing to address here, that is, now that I have the general solution y sub g of x equals c1 e to the x plus c2 e to the 2x, we want to use our initial conditions. Y of 0 equals 1 and y prime of 0 equals 0. So y of 0 equals 1. We'll plug 1 in for the output and 0 in for x. That's going to be 1 equals c1 e to the 0 plus c2 e to the 2 times 0. So 1 equals c1 plus c2, because e to the 0 is 1, so those will just go away there. Now I'm going to take the derivative of the general function, y sub g prime. We've already done that on the left, but I'll just copy it down for our purposes here. Y sub g prime of x equals c1 e to the x plus 2c2 e to the 2x. And we'll plug in the initial condition y prime of 0 equals 0. So we'll get 0 as the output, c1 e to the 0 plus 2c2 e to the 0, or 0 equals c1 plus 2c2. All right, so we now have two equations and two unknowns, and these are linear equations, so we could solve this a number of different ways. We're going to do this now using linear algebra. So we're going to take this, and I'm going to rewrite these c1 plus c2 equals 1, and c1 plus 2c2 equals 0, and rewrite this using a matrix of 1, 1, 1, and 1, 2, 0. So here we have an augmented matrix, and I'll use row reduction. The first thing I'm going to do is I'm going to go row 2 becomes negative row 1 plus row 2. And that will give us, the first row doesn't change, 1, 1, 1. And then we get 0. And then when I go negative 1 plus 2, I'll get a 1 there. And then negative 1 plus 0 is negative 1. And now I want to clear out the 1 in the top right of the square matrix here. And so we will get from this 1, 0, 0, 1. The bottom row is not going to change. And what we're going to do is we're going to take negative, or R1 is now going to become negative R2 2 plus R1. That'll give us that 0 in this location, and then negative R2 is going to be a positive 1 plus 1 gives us a 2. So this shows us that 1C1 plus 0C2 equals 2, and 0C1 plus 1C2 equals negative 1, or to simply say that C1 equals 2 and C2 equals negative 1. We'll take these and plug them back into our general form to show that our particular solution that we're looking for this initial condition is going to be C2 e to the x minus 1, or just minus e to the 2x. And this will satisfy our initial conditions.